This is AP Chem Stoichiometry. We're going to perform stoichiometric calculations, explain the difference between a limiting reactant, excess reactant, identify the limiting reactant, determine the amount of the excess reactant, and compare and contrast the theoretical, actual, and percent yields. So here's our first reaction, and what we have to do is write the equation. And if we read this, we'll notice that we have 25 grams of iron plus 129 grams of sulfuric acid. And they actually tell us that it's going to yield hydrogen gas plus iron 3 sulfate. So we're going to write iron plus sulfuric acid is H2SO4, yields hydrogen gas, which is H2, and iron 3 sulfate. We have to have a balanced equation in order to go forward and do stoichiometry. So we have 2 irons on the right, therefore we'll put a 2 here. We have 1 sulfate, 3 sulfates, so I'll put a 3 here, and then I have 3 times 2 is 6 hydrogen, so we'll put a 3 here. So now my givens are 25 grams of iron and 129 grams of sulfuric acid. So we want to know which reactant is in excess and by how many grams. So we're going to actually stoich from one reactant to the other. It really doesn't matter which one, so you can choose randomly. We'll go ahead and stoich from iron to sulfuric acid. And what I want to determine is, if I start out with 25 grams of iron, exactly how much sulfuric acid is it going to need to react 100% to use up all 25 grams of my iron. So I'll put 25 grams of iron over 1, bring down iron, and we're going to go to a mole of iron. If I want to go to mole, I need the grams from the periodic table, which is 55.85 grams. We're going to bring down mole of iron, and here's where we actually perform stoichiometry, where we'll do a mole to mole ratio from iron to sulfuric acid, and my molar ratio here is 2 moles of iron to 3 moles of sulfuric acid. And now that I've changed over from iron to sulfuric acid, I can bring down my moles and go to grams of sulfuric acid by going to the periodic table, and that's 98.09. So now I'll solve 25 divided by 55.85 times 3 divided by 2 times 98.09, and that's going to give me 65.86 grams of sulfuric acid. Now what you should understand about this is the amount of sulfuric acid that we need in order to use up all 25 grams of iron that's given. The amount of sulfuric acid that we have given to us is 129 grams. So we're going to do a comparison of these. Since I need 65.86 grams, but I have more than enough, I have 129 grams, that means that my sulfuric acid is my excess, which automatically means that my iron here is my limiter, my limiting reactant. So now I want to determine by how much is this in excess. So I'll just compare. If I have 129 minus how much I need is 65.86 grams, so my leftovers is going to be, after sig figs, 63 grams of excess sulfuric acid. So that's the amount that does not get used up in this reaction. Here we have 45 grams of propene. It combusts with 1.75 moles of oxygen, and it's going to yield water and carbon dioxide. Notice they didn't tell us that it was going to yield carbon dioxide, but that's something we know because it's a combustion. So propene plus oxygen will yield CO2 plus H2O. We're given 45 grams of propene and 1.75 moles of oxygen. We want to determine the limiting reactant and we want to know the theoretical yield of water formed. Notice they didn't specify in what unit, so we'll just solve it in moles. But you can solve it to grams too if you want. Alright, so now, first thing I need to know is which one of these two is limiting and which one is in excess. We're going to stoich from one to the other. I'll just stoich from propene to oxygen. If I use 45 grams of propene, then how much oxygen will it need to combust by 100%? So we'll put 45 grams of propene, C3H6 over 1. Bring down grams of propene, and we're going to go to a mole. Go to the periodic table, and that's 42.09 grams. Now, this is where stoichiometry actually occurs. We're going to do a mole-to-mole ratio of propene to oxygen. And again, we need to have a balanced equation first, which we don't have yet. So let's go ahead and balance this equation. And 3 carbons on the left, so we need a 3 on the right. 6 hydrogens on the left, so 3 times 2 is 6. Now I have 6 plus 3 equals 9 oxygens, which would mean this is 4.5. We don't want to have a 4.5, so we're going to double all of our coefficients. That makes this a 2, makes this 9. 2 times 3 is 6, 2 times 3 is 6. So my coefficients are 2, 9, 6, and 6. That's also my molar ratio. So we have a 2 to 9 ratio from propene to oxygen. Notice that they gave me the amount of oxygen in moles. So I'm going to stop at moles so that I can compare moles of oxygen of what I need to moles of oxygen of what I have. So when we do this math, we get 4.8 moles of oxygen. And again, that's how much we need of oxygen to react fully with the 45 grams of propene that we're given. How much oxygen do we have? We have to look at what we were given, and that's 1.75 moles. So I need 4.8, but I only have 1.75, which implies that I don't have enough. I need 4.8, but I don't have enough oxygen to meet the need. Therefore, my oxygen is my limiting reactant, which means my propene is in excess. So now that we know we've identified our limiting reactant, you always want to solve any theoretical yields using the limiting reactant. So I'm going to now use 1.75 moles to solve any more problems. We do have one more where we want to know the amount of moles in water that's produced. So I will take my limiting reactant, 1.75 moles of oxygen, and we will stoich from oxygen to water. So bring down moles of oxygen. Again, this is where our stoichiometry occurs, when we do the mole-to-mole ratio. So moles of oxygen to moles of water, that is a 9 to 6 ratio. 9 to 6. And then we'll stop right here with to get our answer. We end up with 1.2 moles of water. You could also convert that to grams, and that would also be considered an acceptable answer. 78 grams of potassium chlorate decomposes to form potassium chloride and oxygen. So they're telling us that this is our reaction. We need to balance the equation, and we'll have a ratio of 2 to 3 moles of each of these. We are given 78 grams of potassium chlorate, and we want to know how many centimeters cubed of oxygen will form. So question mark centimeters cubed. Also notice this reaction is only 89% efficient. I'm going to stoich from the potassium chlorate because it's my only reactant, therefore it is the limiting reactant by default. So stoich from 78 grams of potassium chlorate to centimeters cubed of oxygen. And so we'll do 78 grams of KClO3 over 1. Bring down grams, and we're going to go to 1 mole. And the number of grams will be 122.55. Times, draw a line. Bring down moles. Here is where stoichiometry occurs. We want a mole to mole ratio. The ratio is 2 moles of potassium chlorate to 3 moles of oxygen. Times, draw a line. This is something that you may or may not recall. We're going to bring down moles of oxygen. In 1 mole of any gas at STP, there are 22.4 liters of that gas. Times, draw a line. Now we can go from liters to cubic centimeters because we know in 1 liter there is 1,000 centimeters cubed. This is going to give us 21,000 centimeters cubed, and that's rounded off to significant figures. So 21,000 centimeters cubed of oxygen. Now I want you to know that this is called the theoretical yield, where mathematically on paper, in theory, if everything worked out at 100%, this is what my yield would be. However, this is only an 89% efficient reaction. So I'm going to take my 21,000, my theoretical yield, and I'm going to multiply that times 0.89 because I want to know how much is 89% of this. And then we're going to get 19,000 centimeters cubed. And this number represents my actual yield. So even though theoretically we could have produced 21,000, because it was only 89% efficient, we actually only yielded 19,000 cubic centimeters. And as a reminder, if you don't recall, to find percent yield, we do the actual yield divided by the theoretical yield times 100, and that equals the percent yield. So 89% was our given percent yield in this scenario. Okay. Methane undergoes combustion to form CO2 and H2O. And we want to make sure it's balanced first. We have 1 of each carbon. We need a 2 here for 4 hydrogens on both sides. This gives me 4 oxygens, so we'll have a 2 in front of oxygen. We're given 12.0 grams of methane and 24.0 grams of the oxygen. We want to know the theoretical yield in liters of the carbon dioxide and identify the limiting reactant. So first, we're going to stoich from the methane to the oxygen. So I'll have 12.0 grams of methane over 1. Bring down the grams of methane. We're going to go to a mole of methane, and that's going to be 16.05. Bring down mole. And here's where we will stoich from methane to oxygen. And it is a 1 to 2 ratio, 1 to 2. We're going to go all the way to grams so we can compare our answer to the given amount of grams. So 1 mole of O2, we're going to go to grams of O2, and that's going to be 32 grams on the periodic table. This is going to give us a yield of 47.9 grams of O2. And so now we want to compare where this is the amount that we need. However, the amount that we have given to us is the 24.0 grams. And so if we look at these, if I need 47.9 but I only have 24.0, this is going to make our oxygen the limiting reactant. Therefore, we're going to use our limiting reactant in order to find our final answer. So we'll put 24.0 grams of oxygen over 1, times, draw a line, bring down the grams. We're going to go from grams to moles, 32 for oxygen. Bring down moles, and this is where we'll do our stoichiometry, and we're going to stoich from moles of oxygen to moles of carbon monoxide. The ratio is a 2 to 1 ratio. So we'll put 2 to 1. Times, draw a line, bring down mole, and here they ask us to go to liters. So we'll put liters of CO, and liters is going to be 22.4 liters because 1 mole of any gas at STP is equal to 22.4 liters. The answer to this is going to be 8.4 liters of carbon monoxide.